So today, Dr. Shen will speak to us about the gap between academic research and industrial practice in operations management based on his own professional experience and observation. As he calls it, mind the gap. So Max, I know you are extremely busy, so thank you very, very much for spending time with us tonight. And the podium is yours, and whenever you are ready.
Okay, thank you, Professor Yu Ding. I have to declare that actually I know Professor Yu Ding for a long time. We went back to graduate school in Tsinghua. But the reason he invited me was not because we were classmates, was really because we talk about operation research and the gap between research and practice. Because I had so many consulting experience in the past. So when we chat, we always chat about the gap between research and practice. So he kindly invited me to contribute a paper in his journal, the flagship journal of industrial engineering, IISE transaction, and I happily wrote the paper with my colleagues Chen and my student Tianhu and his student Yi. So in this paper, we want to just to briefly talk about why industrial engineering and operations management has not been so popular in industry, and then what we can do to make our discipline more relevant in the industry. So today I only have about 1 hour. I just want to share with you some of my own experience, and some of the opinions might not be politically correct or suitable. But I just want to share with you from my many years of consulting with IBM, with GM, with Alibaba, with GD, how I see operations research and operations management can contribute, and why we haven't contributed enough in this area. Okay, so I want to treat this as an open forum. If you have any question or debate item, I welcome your comments and questions. But give me about 45 minutes. Let me finish my presentation, and then we can have another 15 minutes for discussion. So let me just go to my talk. First of all, I really want to thank the Institute of Industrial and Systems Engineering for leading this initiative. After Yu Ding became the editor-in-chief, he did so many initiatives trying to IE more relevant. And I think between our discipline, which is industrial engineering, and practice, there are actually considerable gaps in between. But if we look at the gap, actually, we'll figure out, what caused all the gaps. The reason I picked industrial engineering, maybe we didn't the same reason, because we studied mechanical engineering in Tsinghua. But then we switched to industrial engineering because we believe that industrial engineering and system engineering should be the discipline that makes things better for any industry. Right? That's why we switched. And also our specialty should be solving complex problems. No matter what industry, what complex problem you have, we can always make it better. That draw my attention, and I never regret that I switched from mechanical engineering to industrial engineering. But in practice, actually, you can see that many of us try to work on some really fancy models. But then, sometimes the model will not work in practice, right? Why this is the case? Because sometimes our model might be too simple. First of all, everybody knows that there's a famous saying that every model is wrong, but some models are useful, right? If you look at the IISE definition of our discipline, actually it's clearly mentioned that we should draw upon specialized knowledge and skill in mathematical, okay? Not only mathematical, but also physical and social sciences, together with the principles and method of engineering analysis and design to specify, predict, and evaluate the results to be obtained from such systems. I think what happened in the past, and many of the young scholars, is that we probably only focus on one particular aspect of the model. I do know many of you want to work on the pure mathematical model, but if you ignore the physical model or the social sciences aspect of the model, then probably your model will not be so correct, right? I think that's one of the main reasons that we are not so popular in industry. Okay, so I want to mention many of the failed implementations of operations management models. And if you work with those industries, you'll find out that nowadays everybody is using computer science, AI, machine learning. Even in some domain knowledge in chemical engineering, they work with chemical engineers, not industrial engineers. Why? Because we specialize only in one particular aspect of the model. We care about the model so much. This is why I put the model here. Sometimes we would ignore the real aspect of the real problem. Okay, so let me give you some example in the next 40 to 45 minutes. But I want to caution you, you have to mind the gap. Otherwise, we would keep on publishing papers in top journals, but industry people will never read our papers. You know, this is embarrassing, but it is really the case. So based on my own experience, I felt that there are three bottlenecks that prevent us, industrial engineers or operation management people, to apply our domain knowledge to real problems.
是的，我觉得就是第二。
Thank you for your comment. But let me, Professor Yu Ding, you probably want to mute everybody. But so let me try to finish my conclusion. I think there are three major bottlenecks. First of all, is that it's difficult for us to verify the performance improvement. We always came up with an exciting model. We tell them CEO that, look, my model is perfect. If you use my model, I will improve the inventory cost by 10%, or I will reduce your cost by 20%. But then how do you verify this? This is the first bottleneck. Secondly, is that we have to build trust between our own algorithms and then the people who are actually on the ground. Are they going to use our algorithms? Are they supporting our algorithms, or maybe not? That's something we have to pay attention to. And then the third thing, especially for a lot of young researchers, that we have to balance the model accuracy and simplicity, because sometimes we want to build a simple model, we can derive a lot of exciting results, properties, but then the model might not be so accurate in practice. So in the next 40 minutes, I will delve on those three major gaps. Okay, so it all comes from the model, because we live and die with the model, right? And everybody is so excited about our operation research model. But in the three phases of the model, we all make mistakes. Well, first of all, in the development of the model, sometimes if you can imagine, if you think about all the model you have run into, especially for people in supply chain management, the model you typically use are the new winter model or the simple inventory models, right? But then when you try to sell these models to the managers, most of the time the manager will tell you those models are too simple. And we look at single period models, but no company live on single period. They live on many, many years, right? And then when you try to implement your model, it might be more complicated than news winter model. Most of the time don't get the user inputs. So we don't get the trust when we try to implement our models. And then, supposedly, everybody goes along, they are your best buddies. They trust your model, they trust your implementation, but then how do you show your model actually works, right? So those are the bottlenecks, those are the difficulties. And I will actually tell you that because of those three bottlenecks, there are opportunities actually can make all these bottlenecks go away. And by the way, those bottlenecks are correlated. It's not just one issue. Because of you have such a simple model, it caught all the other problems. Okay, so I will use all the 3 bottlenecks to draw the opportunities for us actually to do better. Okay, so I will try to maybe to do this 3 bottlenecks one by one. Well, first of all, I want to share with you how to verify the performance improvement in real industry. Okay, and actually this is not my own creation. In fact, I check that most of the papers actually, more than 70% of our supply chain simulation papers actually do not use real data. We actually just create our own data and simulate and then compare and then claim our models are the best. But how can you convince the people who are actually doing the real job that our model are relevant? Okay, and then we don't do real experiment. What I mean by real experiment is that it's an algorithm you design, you put it online. So Alibaba or Amazon will use your algorithm online, actually in real time, to help them do business. We don't have so many of them because we never convince people to convince them to use your own algorithm, right? So this is why when we come up with new models and all the exciting results in industry, they don't use our algorithms, right? This is really bad. And then so this is why a lot of managers will actually they may like our model, but they actually may not use our results. So that create all the gap between our model and the real implementation. So why this is an opportunity? Because nowadays with a lot of e-commerce opportunities for supply chain, actually you will have a lot of operational data. And then the other thing we typically ignore in operations management is that we don't take in users' behaviors in our model that much. That's why the users actually don't believe in us. Okay, so this actually creates an opportunity that we can use all this operational data and also take into consideration of the user's behavior and to do a better data-driven decision models. Okay, so first of all, you can use all the historical data, try to verify the performance of your proposed algorithm. And many of you take OR operation research 1 or 2. You all know that we don't work with data. We just come up with a linear program. We assume we know the parameters, we know the objective function. We just try to solve the problem. But now with all this data, it's a time for us to actually use all the data without making all the assumptions, so that our result can be more convincing to the people on the ground. And then actually by learning all this data from the past, actually you can make better decisions in the future, right? So this is actually what I want to show you, that there are a few projects I was involved that we actually use data-driven method, not the typical LP, IP that we learn from textbook. And the managers are really happy with our results. So and then I think many of you also know that field experiments is the key for us to convince the manager that our models are relevant, right? But I would assume that everybody knows what is a field experiment, right? Basically, it's a method for testing causality and the real scenarios, right? By randomly assign the subjects to treatments or control groups, right? So this way, we can get over all the bias or all the assumptions we may make that the manager may not like. So if you can design a good field experiment, is the best way to convince the manager to believe in you. Then in recent years, if you look at all these papers I cited here, our researchers have been applying all these field experiments to Zara, to Airbnb, Alibaba, Amazon, and my team also applied to JD.com. And then let me just, I don't have enough time, but let me show you how we did this project with JD.com and then how we convince them to finally use our algorithms in their daily operations. I think many of you probably know JD.com, but if in case you don't know, let me just briefly introduce the company and then the research problem. So JD.com actually is the largest retailer in China, right? And it's the third largest internet company globally. And they have more than 570 million active customers. And they have global network with Tencent, with Walmart and Google. And what's most striking is that they promised, and they did this, 90% of the orders will be fulfilled within 24 hours, right? If for people who are from US, you probably know that when you order something from Amazon, normally you will get it in 3 days, sometimes 4 days, 5 days. But in JD.com, is 90% of the orders will be delivered same day or maybe next morning. Okay, so if you look at their network, you can think of JD.com as basically Amazon plus UPS, right? This is why they can promise all the customers they can deliver most of the orders within 24 hours because they have UPS with them too, right? And they have a really complex network with more than 500 warehouses in China, right? So the planning for the supply chain is very complex. And then when we work with JD.com, the problem they give to us is exactly this. How do we promise the same day or within 24-hour delivery for 90% of the orders? Well, in fact, to do this, you got to have sufficient inventory at the right location, right? So inventory management is critical for this promise. But then if you look at the JD.com situation, it's really a complex problem because the demand and when the lead time are very random. And then, JD.com sells more than 100 million different SKUs. For people who don't know, SKU is a store keeping unit. Basically, every different product have a unique SKU number, right? So if they are managing more than 100 million different SKUs, how do you manage all these products to the perfection, right? And then different products have different patterns. Some of the products sell so easily, you put it online, it will be gone in the next 24 hours. But then there are some long tail products. You put those products online, it takes weeks or months to sell those products. So demand forecasting models are so different. And then, how do you actually manage all these hundreds of millions of products is so difficult. And then if you use human beings to manage all these SKUs, a good salesman, a good inventory manager can actually manage 200 different SKUs. This is not easy because for each SKU, for example, this black Huawei phone, you can see on the screen, but what do you need to do? You need to do forecasting of the demand for the next few weeks, for few days, few months. And then you need to plan how many you need to keep in all these warehouses. And then a customer in Beijing or Shanghai order it. How do you make sure you will deliver all these products from the right warehouse to the customer within 24 hours, right? This is not a trivial thing because there are so many different customers. Did I mention there are many millions of customers in China, right? So that's for just one SKU. If you have 200 SKU, this person will be very busy every day to managing the forecasting, inventory planning, and transportation. Now, I already mentioned there are more than 100 million different SKUs. If one person can manage 200 of those, how many people you need to hire, right? So this cost will be tremendous. So JD.com talked to us and asked us whether we can come up with a AI solution, automatic solution that can manage most of the SKUs to the right, precision, and they don't have to hire so many people. So that was the research problem, right? So based on this request, actually, we dive into the ocean of data in GD because they have so many data. And they have every transaction recorded on the cloud. So how do we work with the data to come up with different demand patterns for different SKUs? And how do we forecast the lead time from the supplier? How do we forecast the transportation time from a particular warehouse to a particular customer? All this need our own specialized algorithms, right? So this is, you can already sense this is not an easy problem. So in the end, we came up, we don't have enough time, but we just want to tell you that we came up with actually a pretty beautiful model where we apply deep learning and our own domain knowledge in inventory management. So that's an end-to-end model that will take all the historical data from GD.com, will analyze all the data, and then our algorithm will output the order quantity for different SKU for every different order cycle, right? So this sounds simple, but for the machine learning to work really well, it's a good marriage between operation research and AI. And this is the main message I want to deliver to you, because how do you actually combine AI and domain knowledge to come up with a good algorithm? Because even in our own area, in operations research, OM or industrial engineering, basically there are a lot of people thinking that maybe we don't need IE anymore because all the AI models will take over industrial engineers. They can learn everything and then they can do better than industrial engineers, right? So there's some debates about whether our discipline should continue to exist, right? Maybe in the future, I cannot say for sure this won't happen, but I think in the next few years, until I retire, I think this is not going to happen, because a lot of AI algorithms actually, they don't have the domain knowledge. So when they actually try to solve the problem, they are trying every possible scenario, and it will take them a lot of time. And also, they don't have the right features. So I will show you in the second problem. Because we know the domain knowledge, actually, our model will perform better than a blind AI algorithm, right? So actually, so this is the key for our end-to-end framework to work well, because we actually use a deep learning model, but also we use our domain knowledge to train the model better so that the learning method can work so much quickly than a pure black box AI algorithms. And also, we actually can speed up our algorithm even further in the overall optimization problem. So this is what we did. If you are interested, you can check out our paper. Is there a question?
No, sorry, there's still the unmuted thing.
Okay.
Yeah.
You can use AI to mute everybody.
I use a human eye to mute it. Go ahead.
Or you can
Sorry.
announce that maybe people should mute themselves until I don't know, 9:50. Okay. But okay, so we came up with a really beautiful algorithm. We were so proud of this, but then it's another matter to convince the managers to use our algorithm. So how do we convince them to use our algorithm? First of all, we will ask them, so, okay, so for this problem, what kind of algorithm you are using? So they'll tell you, all the different policies they are using, the best one, the worst one. We collect all of this. And then we did a lot of offline simulations, trying to show that, for all your algorithms, our new algorithm can beat you offline, for all this historical data we have. So we did a lot of these offline experiments. Eventually, they were convinced that, yes, our algorithm indeed is better. And then we actually did a real field experiment actually in 2020 for 2 months. We tried, we put all the data from 12 DCs at more than 9,000 SKUs, right? So we compare with basically their best algorithms and with our end-to-end algorithm. And we show that our algorithm actually significantly reduce all the matrices, inventory holding cost, penalty cost, and overall delivery time is all up by a
Recording in
major
progress.
amount. Right. So, and with this experiment, many of the managers were convinced that we indeed have something pretty nice. So we, then we try to convince them, how about we put this system online? And, they were cautious, but we convinced them to put this with some SKU. It worked really well. And then they expanding this to more than 9,000 SKUs. And then actually, realize the dream we talked about before, because now they can use our own algorithms without real people to manage their the inventory for 9,000 SKUs. And this technology actually was shortlisted for the Gartner Power of the Profession Supply Chain Award. We were there with Johnson & Johnson, GE, and some other major firms in US and Europe. So we are really proud of this. And then it actually took us 2 years to finish this project. So, I really want to thank my team, especially, my own PhD students and the co-worker from GD.com for their patience, because we really want to go from offline experiments to a real field experiment and convince everybody to go along. And then now I believe they are expanding this to further SKUs. And also we are also refining our end-to-end algorithms. I do believe there's a hope that our algorithm can, in the end, be the AI solution for millions of, hundreds of millions of different SKUs management in GD.com or in any other platforms. So I don't have the detail here with you, but for people who are interested, you can check out the paper in Management Science, where we have a lot of details about this. But again, the idea is this, is that, for OR and OM people or industrial engineers in general, in the past, we were happy with our own model. We are happy with our own assumption. But nowadays, I think it's really the time for us to go work with real industry, get their real data, and then design a data-driven algorithms and convince them to use our own algorithms. We did this, as I mentioned earlier, many people did this for Alibaba, for Airbnb. I do hope there are more people who can expand this outreach to more companies. Okay, so let me share with you some major takeaways. I think if you read all the inventory management papers from all the top journals, you will find out that most of these papers were trying to prove some optimality results. But then when you apply this model to real industry, the first thing we will ask is that, how do you calculate the holding cost, right? It's not that simple. How do you calculate the penalty cost? Is even worse. Nobody knows. So we have to collect all this data from real users, from real platform, and then come up with the right value of the holding cost and the penalty cost. And actually, this is why this is hard, because this is a project that has to be initialized by the CEO. Because if you have to get all the data from transportation, from warehouse, from all this personnel data, without the CEO giving orders, you don't get all this data, right? So if you calculate the holding cost in the warehouse, you need to know all the electricity usage, how many people were hired in the warehouse, how long the inventory was kept in the warehouse. How do you get all this data? You have to get the permission from CEO. This is why our discipline is so difficult. Even the holding cost is not very easy to be calculated. And then penalty cost, how do you do this? It's not that easy. Well, I don't have time to talk about this, but I want to show you that this part of getting data is actually the main gap separating real application versus a theoretical paper. And then my second lesson, I really want to to share with you is that most of the managers were super critical of any assumption you make. We were so getting used to making the assumption of the demand being normal, is ID, the holding cost is a constant, demand is seasonal, but probably there are only 3 seasons. All this, let me tell you, will not work in real life because this is not the case, right? So how do you actually get all the data and then can work with all the real people to have your assumptions in the right place? It is really the second lesson you have to learn, right? Without the right parameter in your problem, your result will be wrong, right? So even the penalty cost in holiday seasons versus a regular day to sell, if you buy a gift for your loved ones for Christmas, if they don't get delivered before Christmas, the penalty is much higher than if you order it in February and nobody care whether it get delivered, right? So all this sounds common knowledge, but actually when you work with the real industry, all these parameters have to be validated in real time. And then it's even more difficult to convince them to actually go your way, because for this inventory problem, if you work with the business manager, the one who manages the actual platform or the offline shopping outlets, they don't care about whether you want to keep safety stock or not, because they just want to make sure for the next week they have enough inventory. How do you convince them you should keep some safety stock so that when next week there'll be more people coming to buy, right? All this, you got to figure out who is the right level of management, and you should talk to the right level of manager to let them go with your idea. So all this is actually only when you work with real company, you'll figure out all these are not written in any textbook. Okay, so let me stop here for the first gap. Let me go on to the second gap. The second bottleneck is that actually I think is actually very important. How do you convince people to use your own algorithm? Basically, how do you let people trust your own algorithm and make it online? Right. So in fact, it's very interesting after I work with so many companies that actually there are a lot of information mismatch between the user and your own algorithm. For example, if you work with a warehouse, if you want to tell the workers in the warehouse, those people who are doing the packing, right? So when you order 3 items, they need to come up with the right size of the box to put all the items in the box. And the question is, what size of the box they should pick, right? And you have a fancy algorithm, 3D bin packing. You tell them, look, use my own algorithm. I can, save you 20% cost. But actually, when you show the algorithm to the worker there, they will not use it because they have a lot of knowledge than you about the items. Because some of the items are fragile, so they don't want to put it in the bottom of the box. And some of the items have an edge, even though the size is not big, but if you don't pack it in the right way, it might get damaged. Also, you cannot put this in the algorithm. So when you came up with the algorithm, ignore all this. Trust me, nobody will use your own algorithm. Okay? And then similarly, most of our models are so complex. What we did was just come up with a linear programming integer program, and then just tell them, look, you should follow my recipe. But then, keep in mind that, people tend to reject what they do not understand. If you just let people trust their instinct or trust that, your algorithm is the best, they will not do it. Okay. So what happened is that in real warehouses, most of the work actually will choose larger boxes than the one that you tell them to do. Why? Because first of all, they don't trust you. Secondly, in some of the cases, if your algorithm has the wrong answer, then they have to put out all the items they put in the box and then repackage. That will deliver their time, and their salary will be impacted. So they would rather use a larger box to avoid all the mistakes, right? Do we consider this when we design our algorithms? No, we never do this, right? And in the vehicle routing problems, a lot of technical people come up with really fancy vehicle routing algorithms. It's so complicated, nobody wants to use it, right? So, and then, AI is even worse. But we do a fair share of a complex algorithm. We just tell them, trust me, use our algorithm. I'm pretty sure it will save 20% of the cost. But sometimes if you cannot intuitively explain to the manager why we are doing this, then they will not use it. This is why in the marketing, when they have the causality forecasting, they would tend to go with the marketing people because they can explain, look, the economy is doing well. If you increase the price, demand will go this way. But we don't do that. We just come up with a linear program or integer program. We just tell them this is the result. So, if we do this, nobody will be convinced to use our algorithm, right? So those are the challenges. And then what are the opportunities? Well, again, we have to work with data, right? So we have to take into consideration of all the user experience, their information, and we have to put this into our algorithms. I will show you one example how we did this. And then we try to build hopefully a explainable, simple model, right? So the managers can actually talk to his boss to say, look, I think this algorithm makes sense because when this parameter goes up, then this output should be going up too, right? So I think this have a big future in our discipline. How do we build up a explainable optimization plus AI model for different industry, right? Again, how do we actually take all this previously unknown information by learning from the known data, right? All this, if we can build all this into our algorithms, then I'm sure our algorithm will be really popular in real industry. So let me again share with you maybe in the next 5 minutes another project we did with a Chinese firm. Maybe everybody know ELE.B, right? So this is a company that will deliver lunch to you. Hopefully not too much time, right? If you want to order lunch at 11, hopefully it will be delivered before 12, right? And then, similarly, I give a seminar talk at Uber Eats and, DoorDash. They all face the same problem. Basically, they are serving a CBD area. There are a lot of people working here, and they are either they don't want to go out or the lunch time is too short. They want to order, maybe at 11, and then hopefully the lunch will be delivered to them before 12, right? So this company was doing really well. When we work with them, actually, they already have a lot of people, OR people, to help them. Basically, this is a problem, right? So they will have a cutoff time, for example, by 10:15. You have to order before 10:15, between 10:15 and 10:30, right? Or during this time, you will order your lunch. And they will promise you they will deliver before 11:45. So that's a guaranteed delivery time, right? But in real life, is that most of the orders will be delayed, right? And sometimes actually the delay will be so much that you will pass your lunch time. So this is certainly not ideal because you want to, when a customer call you that they want a lunch before 12:15, you got to tell them whether they can do this, whether you can do this or not. Even if you cannot do this, you got to tell the customer, we cannot deliver by 12:15, but by 12:25 the latest, right? That way the customer will trust you. Otherwise, if just they call in and then you don't promise the time, they will not order from you, right? So what happened is that before we were involved, all the order assignments were mainly done by people actually who are doing the delivery. And then we found out that there's more than 20% of the orders were not delivered on time. And then actually the delay on average can be about 10 minutes. And the worst can be 45 minutes or even 1 hour. And then that's certainly not acceptable. Why we have this issue? Because nobody can predict the travel time so perfectly, right? Well, I took it back, the delivery time, because the delivery time actually have two components. One is actually the driving time from the restaurant to the work location, right? But then there's also the service time, because if this customer is on the 18th floor, you got to deliver either to the first floor or the 18th floor, depends on how the arrangement, right? Sometimes the company have a delivery box on the first floor. But in any case, you need to know all the service time before you can promise the customer how much time it will take you to deliver. And then, the travel time en route, actually, this is a famous traveling salesman problem, we call routing problem. We have so many algorithms to solve this problem. But before us, most of the algorithms they use were not doing well. Because, if you work on we call routing problem, traveling salesman problem, you all know we make so many assumptions. We would assume that, travel from point A to point B will take 5 minutes. But actually, that 5 minutes will depend on the time of the day, right? Secondly, you would assume that driver will follow your route, but sometimes the driver will not follow, because actually they know the traffic time better than you, right? They will know during 10, maybe in the morning, 10 a.m., taking this route is much better than taking, another route, which will give you a much longer delivery time. But then at 3 p.m., maybe this route is better. No algorithms will take all these complications into consideration when they design the vehicle routing problem. Because in the end, it's a vehicle routing problem, because you need to know how long it will take you to deliver all the food to the customer. And then after you know how long, you can quote those numbers to the customer, because you know how much time it will take you to deliver to the customer, right? So, even though we have very well-designed algorithms, but those algorithms will not work well because we don't know all this randomness in travel time and service time, right? And then sometimes if the driver doesn't know the location very well, even though he's in this building, but he may it's A or B or C, the different zones also will take him a lot of time to find the right building, right? All this time you have to know, otherwise your estimation will be off the target. So, this is a typical model you will build. Everybody who study operation research will know this is the right model to do. But the key is there are so many random parameters here. A certain service time at a location I, the delivery time also will be very random. So how do you solve this problem so that you can have a really reliable estimation of the delivery time? Right, so as I mentioned earlier, if a driver have to deliver to 6 different customers, using our traditional traveling salesman problem, we know the distance between all the customers, and we can estimate the travel time, and then we'll come up with the optimal algorithm. This never works well in real time, because sometimes the driver actually will not go with this sequence. They actually know that at point 4, if he goes to 0.5, then to 2, then to 6, actually, he believes him actually might be better, right? So they will deviate from your solution because they don't trust your algorithms, right? So we have to look at the historical data to see how the drivers actually learn from the different environment and take their own decisions. And if we can learn this behavior, our model will be much more accurate, because in the end, it's these people who are actually deliver the food to the customers, right? So, and this is just to show that actually, if you just use the best traveling salesman problem algorithm, that it will be very different from the actual delivery time. So in the end, again, we combine AI models with machine learning. We pick among so many different models. Again, we try to make this, right? There are 3 measurements. First of all, you have to be quite accurate. Secondly, it has to be a trackable solution, meaning that you can very easily solve the problem. And then you can easily interpret this result to the driver so that they will believe in your algorithms, right? So with these three objectives in mind, our optimization model and AI model will be quite different from the traditional OR model. So we picked this because it have a trackability and also very easy to explain this to the drivers. And here I want to show you that actually because of our domain knowledge, actually we came up with a feature that machine learning people actually were not so easy to come up with this feature. For those of you who know, if in an area, if you have endpoints, then the total travel distance or to visiting all the endpoints actually is proportional to the square root of n. N is the number of points. So this is something we learned from our traveling salesman problem. And then we actually build this into our feature, right? So this square root feature is built into our model. And so our lasso model actually, with these features, actually perform much better than the machine learning AI people who would never come up with this kind of feature. Or they may try, but if they don't have the domain knowledge, it will be really, really difficult for them to come up with this feature. So with this feature, we come up with a nonlinear model. Again, I want to mention this, is that most of our people are comfortable with just linear program. But sometimes, with real problems, the problem become nonlinear. But if we can have a better way to handle nonlinear terms, then again, we have an edge, which will help us beat the computer science people who probably will not be so familiar with solving this kind of nonlinear integer programming. So in any case, we came up with a really simple lasso model with only 6 terms, and with this feature that only TSP people would know. And then our model is so easy to explain to these people because all these terms are linear, and also we can have a way to linearize this nonlinear term. So in the end, our model actually, first of all, perform much better than any existing algorithms. And then we capture the driver's behavior in practice because our model actually learned from all the data, and we capture this in our lasso model. And then actually our model, you can see, we only need to estimate a few parameters, up to 5 betas. So our model is much simpler than the traditional AI model. And then we perform better, and it takes us less time to solve the problem. So this is the whole message I want to deliver to you, that if you try to solve a real problem for the industry, the model probably will end up to be really complex, right? But don't be scared, because we can use our domain knowledge, try to come up with better features, and try to come up with easily solvable algorithms, so that our algorithm will perform better in accuracy and also solution time. So again, this paper is published in Management Science last year. Was motivated by the food delivery company case. I'm not sure I have enough time, but let me just quickly use next 2 minutes to talk about the other gap. Is that how do you balance the accuracy and simplicity of the model? Because everybody likes simple model, but if the model is too simple, then probably accuracy will be suffered, right? So how do we deal with this? As I mentioned earlier, I will quickly go over this, is that, with the AI model I talked about in the last 2 case studies, you can actually come up with a data-driven decision method that can try to get over all these 2 bottlenecks, right? All these two gaps. The key is, how do you come up with the right AI plus optimization model by utilizing your domain knowledge so that you can solve the problem much better. But most of you, I think, hopefully, I don't know the audience, but some of you probably are still learning machine learning because we are the traditional industrial engineering discipline. Many of the people probably still use traditional method. So I want to actually share with you a different approach where we can trade off accuracy and simple formulas, and it still works well in industry. So very quickly, I want to talk about a project we did with Chinese natural gas company, where we actually try to optimize the natural gas supply for different cities in China. But to do this, again, this is, for industrial engineers, we are supposed to work on any industry, right? Any complex problem. But in reality, most of people will avoid complex problems. We only want to work with linear program, integer program, network flow models. But so this model will serve as a good example that we actually work on a really messy problem where you have to know fluid dynamics, thermodynamics in this optimization model, because to make a natural gas flow in the pipeline, you have to have the right pressures of the 2 points, also the right temperature, so that the gas can flow in the right direction. Those of you who study mechanical engineering will know this. But then if we add this into our optimization model, it becomes so complex. We don't know how to solve this, right? But then in many of our top journals, will not take a problem that doesn't have closed form formula, doesn't have optimality proof in their journals. I think this is actually very wrong. And the editor-in-chief for IISE is here. Hopefully he will take more papers that we try to solve real problems. Because otherwise we will be narrower and narrower. We only try to solve the problem that we can apply our tools to, right? So for all these messy problems, who solves this? It's the chemical engineers, the petroleum engineers, not us. But we have to fight to get back all these problems, because otherwise, we will become famous in solving linear programs or integer programs. But all these nonlinear problems, they have their domain engineers to solve this problem. But anyway, I don't have time to go over all the details, but I want to show you an example that we actually try to use this formula where we model the flow between two locations, I and J. So Fij is the flow between two nodes, I and J. And it depends on the pressure, Pi and Pj, and there's a constant beta Ij. This is the most simple model you can take. But actually, it didn't work well for us, because in China, the elevation of 2 points can be huge, right? So we have to consider the difference in the elevation of the different of the two nodes. So actually, we came up with a different model by modeling the alpha Ij, which is the elevation difference between I and J. This is more accurate. We show actually it worked much better. Okay, if you look at the graph, you can see this is the equation that take into consideration of the elevation gap. It performed better in terms of errors. But then with this extra parameter, the problem becomes harder to solve. Actually, it becomes even harder if you consider the temperature at the location, because if the temperature at location I is higher or lower, it will impact the flow of the natural gas. So ideally, if you can have to consider the temperature Ti is more accurate, but then the problem becomes more complex. So you got to have this trade-off, right? To have from the simple solution, simple formula to the most complex formula. And then you have to, depends on your application, pick the right one so that it has the right error range, and the manager can actually follow your model, because you have to be able to explain to the manager why your model makes sense. So for example, if you are in a flat area and the temperature are roughly the same, of course you will choose this model. But if you choose, an area that I and J are so far apart and the temperature is so different, you got to use this model, right? So there's natural trade-off between a simple model and the accuracy of the solution. And you have to pick the right one for your model, for your application. Wow, I'm running over time. So let me finish it here. This is a quick summary of my takeaway message is that, as I mentioned, there are 3 gaps between practice and our research. And then I mentioned all the 3 gaps here. But if you can come up with a data-driven decision models by doing a nice field experiments, come up with a data-driven optimization and AI model, and then take into consideration of the user's inputs, I'm pretty sure your model will be accepted by real industry. So that's my sharing for today.